Hi there, this is section 8.4, video number 2, and I'm actually going to do most of this under my camera, so let me get that started here. So we're on, in your note packet, page 7. So I believe the first video went through example 4, so I'm going to start here on example 5. So I've filled in some stuff that I was just going to talk through this one, and then you can pause the video and update your notes with this. Let me see if I can get this a little clearer for you. There we go. So this is similar to what you did in examples above, except you notice we have infinity for our lower and upper bound. So you can think, remember the rules for integrals says that I can split two integrals and add them together if the upper bound here matches the lower bound here. So that's what I want to do. So I want to say, I'm saying I'm not going to get to this negative infinity. I'm going to approach it, and I put in that constant there or variable there to take care of that negative infinity as my lower bound. And then you can put any number in here. This should be a 0. Sorry about that. And this should be a C. You can put any number in here, does not matter, but I encourage you to put 0 in because 0 is a lot easier to plug into your antiderivative. So I'm going from C, which is going to be negative infinity, to 0, and then 0 to C over here, and C is going to approach positive infinity. So it's the same as going from negative infinity to positive infinity. And the way I link these two integrals is to put that common number in the middle. So this is my first step where I'm separating that into two integrals with the limit out front. So now take the antiderivative. The antiderivative of this is tan inverse of x. So here's my two limits, tan inverse of x, upper and lower bounds. And then I'm going to plug in, for this one, I'm going to substitute in 0 and then substitute in C. And for the second limit, I'm going to substitute in C first and 0 second. Now, this one, you have to remember what that graph looks like for tangent. So I've sketched it over here for you because let's look at this. So first of all, tan of 0, I'm just going to get 0. So that's going to be 0. And then I'm going to have minus tan inverse of C as C is approaching negative infinity. So think as your x's approach negative infinity, if I'm on this tangent graph, my tangent graph approaches negative pi over 2, never reaches it because it's undefined at negative pi over 2. But remember, I'm just approaching it. So this would be, what I'm getting close to there is negative pi over 2. Now, on the other side, so I'll put this in parentheses, plus, so that's this plus. Now, over here, I'm doing tan inverse of C, but this time I'm on the positive side here, positive x's or positive infinity. Well, tangent gets close to pi over 2 on the positive side, so this would be pi over 2, minus tan of 0 is just 0. So then I can simplify this. So minusing a negative becomes a plus. So I end up with pi over 2 plus pi over 2, which would just be pi. So you would say, because my limit is a number, this converges. Okay, now this next part is saying, what if at one of your limits of integration, you have a vertical asymptote? So it says integrands with indefinite discontinuity. So another type of improper integral happens when our integrand has an essential discontinuity, a vertical asymptote at the limit of integration. So I have a vertical asymptote happening at one of these values. So if you look at this function, this says not including a. The function is not defined here at a. That's because at a, there is a vertical asymptote. So here's kind of a sketch of what that might look like. My function is defined at b, but over here at a, I have a vertical asymptote. So what I want to do for my integral is I want to say, well, I can't actually equal a because I have a vertical asymptote. So I'm going to approach a from the right side because the right side or to the right of a is defined. So that's where this comes from. So c approaches a from the right side. So my a here is gone, and I'm just approaching that a. So on this one, my vertical asymptote is on the right. So this is what the situation would look like. Function is defined to the left of b. So I'm going to approach b from the left. So a is fine. B does not exist, so that's where I want to put my limit in, and I want to approach b from the left. So I would put those sketches in your notes. I don't know about you, but it helps me to have a picture. And then the last one is when you have a discontinuity in the middle. So you can see they're saying, hey, the function is defined on the left here at a, on the right here at b, but in the middle, there's your vertical asymptote. So this one I want to split into two integrals. And again, I want to do that where the upper bound of the first integral matches the lower bound of the second integral. So this is the same as going from a to b with a stop at c in the middle. And then when I put my limits in here, wherever this vertical asymptote is, I'm going to start at a and I'm going to approach it from the left. So c is going to approach this number from the left. And then on the other side, I'm going to start at c and I'm going to end at b. And on this side, I'm going to approach c from the right. So I'm approaching this from the positive side. Okay. Now, this p-series test is in Chapter 8. However, this is like previews of coming attractions for Chapter 9. So I don't want to spend a lot of time going through this. It's kind of like a proof of why this p-series test works. And we'll do the p-series test in Chapter 9. But I'm going to show you this.
Hey guys, we're going to be talking about section 8.4.
Didn't mean to do that. I'm going to show you this PowerPoint of that p-series, and I'm just going to talk over it very quickly. So what I'm doing is I'm checking the limits here for different values of p. So if I approach 0 from the right, this is my function. So this is if p is equal to 1. And this is my antiderivative. Plug in my upper and lower bounds, and I get natural log of 1, which is 0. And then I get natural log of 0, which is undefined. So this is saying, oh, this diverges. We'll use this p-series test in Chapter 9 to decide if a sequence converges or diverges. And this is kind of showing you why that works. This is if p is greater than 1. So here's my antiderivative. Here is my antiderivative again with my limit in here. So you can think if I'm plugging 0 in here for c, this whole term would be 0. This on the bottom, this could be a big negative. So this on the bottom is a big negative. So I'm approaching, technically I'm approaching negative infinity, but it doesn't really matter. If I'm approaching infinity or negative infinity, I diverge. So when p is greater than 1, I diverge. And then down here, it's when p is between 0 and 1. So here's my antiderivative. If I'm taking the limit as c approaches 0, this is going to be 0. I'm going to end up with 1 over this value, p, which is between 0 and 1. So that's just going to be a number. So that will converge. Okay, so if you want to put this in your notes, maybe when you get to chapter 9, you'll remember it and it'll be familiar, but I can tell you for chapter 8, it's not going to come up. Okay, let's look at example 6. So this is another situation where you have a function that has a discontinuity. So if you look at this, what would make the denominator 0 if x was equal to 1? So picture I'm finding the area under the curve between 0 and 3, but my function's not defined at 1. So I kind of sketched it here. So this is 0, this is 3. Here is 1, and there's my vertical asymptote. So I sort of want to find this area and this area. And I can't just go from 0 to 3 because my function is not defined at 1. So you can think about splitting this. I want to go from 0 to 3. I have to have a stop at 1. And what we're going to do is we're going to put a limit in here where we say, oh, I can't actually be equal to 1, so I'm going to approach 1 from the left, and I'm going to approach 1 from the right. So this is what this would look like. I would have, and so where that 1 is, I'm going to stick my C in there. And I'm going to approach 1 from the left. I can keep the 0 in there. The function's defined at 0, but I'm going to put the C up here where the 1 would go. And I'm going to approach 1 from the left of my function, dx, and then I'm going to add what's happening over here. I want to approach 1 from the right. So this would be the limit as C approaches 1 from the positive side. And here's my C, and I'm going to end at 3 still. So upper bound here and lower bound here match. They're both C. Ending at 3, so I'm really going from 0 to 3 of my function. Oops, x minus 1 to the 2/3 dx. So you can do this antiderivative. It is a u sub. I will write it here, and you can check it on your own. Some antiderivative practice wouldn't hurt. I end up with 3 times the quantity x minus 1 to the 1/3 from 0 to c, plus the limit as c approaches 1 from the right side of 3 times the quantity x minus 1 of 1/3 from c to 3. So now I want to take my limit. So I'm approaching 1 from the left side here. Oh, no, I'm substituting in my upper and lower bounds, not taking my limit yet. So limit first, still here. Plugging in c, so I would have 3 times c minus 1 to the 1/3 minus, if I plug in 0 here, if x is 0, I'm going to have negative 1 to the 1/3, which would just be negative 1 times 3, so I would have negative 3, plus limit c approaches 1 from the right, so I'm plugging in 3 first, so if I plug in 3 here, I'm going to get 3 minus 1, which is 2, so I'm going to have 3 times 2 to the 1/3 minus, substituting in c, 3 times c minus 1 to the 1/3. Okay, now we can take our limit. So if c is approaching 1 here from the left, so I'm approaching 1, but I'm not going to be equal to 1. So this would still be 0, because if I'm approaching 1, I would have 0 in here. So I'm just going to be left with my 3 here. Negative and a negative makes a positive. Here I have my 3 times 2 to the 1/3. And if I approach 1 here, again, this whole term is going to approach 0 because I would have 1 minus 1 in here. So you could write this as 3 plus 3 times the third root of 2. Yeah, I mean, you could leave it like that also. Either one is correct. Okay, next one is similar. We have a discontinuity at 2. So this is what I'm doing. I'm taking the area between the curve and the x-axis from 1 to 4. Well, here's my area starting at 1 to my discontinuity. And here's from my discontinuity to 4. So again, I got a break happening here at 2, and I'm undefined at 2. So this is where I'm going to put my c's in. So I'm going to have the limit as c approaches 2 from the left. So that's over here. And starting at 1, going to c of dx over x minus 2. Or that you could do 1 over x minus 2 and put the dx out here. Plus the limit as c approaches 2 from the right. C down here, upper here, and lower here have to match, and I'm ending at 4. Same function. Here, I'll show you what I meant over there. You can also write that like that. Okay, antiderivative is going to be, got to copy that limit again. C approaches 2 from the left. Antiderivative is going to be natural log of x minus 2 from 1 to c, plus my limit as I approach 2 from the right, natural log of x minus 2 from 4 to c. Now substitute in upper and lower bounds. Limit as c approaches 2 from the left. This is going to be natural log of c minus 2 minus natural log of, is this supposed to be negative 1? No, 1. Natural log of 1, upper bound minus lower bound, plus limit c approaches 2 from the right. First, I'm plugging in 4 here, so that's going to be natural log of 2. 2 is positive, so I can get rid of the absolute value, minus natural log of c minus 2. Okay, now let's take our limit. So if I am plugging in 2, approaching 2 from the left here, you can see in your graph that you're down here, you're negative. So I'm going to end up, when I have negative here, natural log approaches, well, I'm going to have a 0 in here, 2 minus 2, and the natural log of 0 is undefined, or it actually approaches negative infinity. So let's just recall natural log. If I'm approaching 0, my natural log is undefined. If I plug 2 in here, I'm going to have natural log of 0, which is undefined. Now, this would be natural log of 1 is 0. But as soon as you get to an infinity or a negative infinity, you can stop. And you can say now that this diverges. Even if we got to it first here, I can stop. If you got a number here and got to infinity here, you could stop. Whenever you get to an infinity for your limit, you can say you diverge. So this diverges. Okay, one more. This is kind of a theorem that says if one function is less than the other function, then if the smaller function, if you want to think about it that way, converges, then the larger function converges. If the larger function diverges, then the smaller function diverges. So here is how, it's kind of a nice way to think about that. If f of x is a short door and g of x is a tall door, So think if I can walk through the short door, I'm short enough that I can walk through the short door. So I'm able to go through the door. So I say I converge. Then I'm for sure going to be able to walk through the door that's taller. However, if I cannot walk through the tall door, in other words, I'm taller than the tall door, I can't get through that door, so I diverge. If I can't get through the tall door, I'm sure as heck not going to be able to walk through the short door. So if the larger function diverges, the smaller one diverges. If the smaller function converges, the bigger function converges. So picture that door thing in your head and that will help. So this says, does this integral converge with this? So first of all, we got to figure out which one is bigger and which one is smaller. So these are fractions. So this is going to have a bigger bottom than this one, which is going to make this less than that. So I'm going to say, if I'm going from 1 to infinity of this function, if this converges, the smaller one, or will converge if 1 to infinity of the bigger function converges. So smaller one converges if the bigger one converges. This is our smaller one, this is our bigger one. So if this converges, this will converge. So I want to show that this converges. So I'm going to do my limit as c approaches infinity of 1 to c. I'm going to write that as x to the negative 2 dx. So my antiderivative, stick my limit out in front. C approaches infinity. My antiderivative is going to be negative x to the negative 1 from 1 to c. Plug in my upper and lower bounds. Still haven't done my limit. So this is going to be negative c to the negative 1 minus, if I put 1 in here, 1 to the negative 1 is 1, and I'm going to have a negative 1. So I'm going to have minus a negative 1. So I'm going to write this before I take the limit. I'm going to write this as negative 1 over c plus 1. So it's just easier to see if the bottom of your fraction is growing to infinity, then this whole thing is going to approach 0. So this is going to be 0 plus 1, which equals 1. So this converges. So we started out showing that our bigger function converges. So therefore, this integral, 1 over 1 plus x squared, the smaller one, converges, or also converges. Okay, that is it. I'm sure you think that is enough.